Hi, I'm Anastasia. I'm presenting our joint work on automatic termination for hyperparameter optimization. In this work, we propose such a criterion for HPOR that is problem adaptive and automatically terminates the optimization process once we are unlikely to improve. What it means, we are going to learn in this presentation. HPOR is a classical example of black box optimization, let's say for some function f, where we sequentially acquiring points gamma t and observe some noise perturbed evaluation of the black box function. For HPOR, that would mean that for some hyperparameters, we define a model that we will then train, for example, via SGD, and observe the model loss, where the loss is computed for the prediction of the model for some input x and a model trained of the data d, and the loss is then computed with respect to the label y. The expectation is over unseen data, and this results in expected loss. The noisy evaluations happen due to the stochasticity in model training, for example, due to stochastic gradient descent. Bayesian optimization is a powerful framework for such black box functions, and we're going to visually recap how it tackles such problems. For some function f with a known optimizer gamma star, Bayesian optimization has a probabilistic model, for example, Gaussian process that takes into account evaluated points, and then acquisition function at each iteration proposes a new input gamma t that's then evaluated and the probabilistic model is updated. Such iterative procedure lasts until a user-defined budget, and then for the best reported solution, we can quantify the convergence in terms of the suboptimality and a function value, which is called regret. The question we are addressing in this paper is when do we terminate Bayesian optimization? And in its core, what we actually want to draw your attention to is firstly, the following question: is this expected loss is what we actually optimize in practical HPOR? Important question, because no, the data distribution is actually unknown and we cannot evaluate the true objective. Instead, we can only evaluate an estimator, which is computed for some new finite data set, validation data set, DV, and then the noisy evaluations that we observe, this noise has two sources, again, stochasticity and model training as before, but also the data realization. In practice, if we want to get better, stable estimator, we would use k-fold cross-validation, where we split the data into train validation and test, and then at each evaluation of Bayesian optimization, we would train k models, and then the estimator would be the sample mean over these models. To sum up, we just noticed that actually there is a discrepancy between a true HPOR objective expected loss and the computable viewer target, right, which is the estimator of this expected loss. And this means that Bayesian optimization is navigated to optimize the computable loss. As before, it proposes some evaluations until the conversions. And though we invest a lot of the resources to converge to some optimal solution, which the conversions we again measure with the regret, it might be the case that optimal solution for the estimator is actually worse in terms of the true objective. And it means that though we launched Bayesian optimization longer, it actually may harm the generalization performance and just waste the resources. And this is one of the outcome takeaway messages of the paper, that actually there can be overfitting with respect to the validation data, and which can be an overseen problem in HPOR. Getting back to the main question of the paper, which is like, when do we actually terminate this Bayesian optimization procedure? When is it enough? And the answer is like once we are likely to improve. And to explain this, what it means, let me draw your attention to the fact that this estimator is equipped with some uncertainty, right, due to the data realization. And we plotted here in the bold orange. More formally, that would mean that if a statistical error of the estimator in terms of the infinity norm is bounded by some epsilon st, statistical error, then the suboptimality in terms of the expected loss gonna be bounded by the sum of the statistical error and some optimality in the estimator. And that leads to the intuitive criterion, stopping criteria we propose, which is stop the procedure once the suboptimality in the estimator becomes smaller than the statistical error of this estimator. That results into the stopping criteria. Unfortunately, neither the left-hand side nor right-hand side are known. And what we propose in our paper is ways to estimate these core values of the stopping criteria. For the left-hand side, we propose to use high probability confidence bounds, which we derive from the Gaussian process model. And for the second, we show how this can be estimated in case of cross-validation. Though, because cross-validation is a well-studied estimator, we know its variance, we know its bias, and what we show in the paper is like how how to use it in our stopping criteria. Additionally, our method allows the user to just specify a tolerance for the solution, and it does not require cross-validation at all. For the experiments, we have a wide range of HPO problems and neural architecture search problems where we show the results of our method, both showing the results when cross-validation is used and when it cannot be used. We compare the methods in terms of relative test error change and relative time change, where we compare this relativeness with the predefined budget of 200 iterations. We have several baselines, those which were available. The first one is convergence I, which is triggered when best remains unchanged for some particular number of iterations. The second one and the third one are probability of improvement and expected of improvement based, where we should define again in advance some threshold values after which Bayesian optimization is stopped. We want to draw the attention that both the methods require specifying this threshold value in advance, and that might be hard for a wide range of problems. And finally, when we plot our method where threshold is derived from cross-validation, it does not actually require tuning anything. The main takeaway from this plot is that our method has lower variance in terms of relative test error change. And it's achieved via adapting the termination to a particular problem. So we do not sacrifice test error change in sake of a speed up. Additionally, we show the results for neural architecture search problems where we use the very same baselines, and in contrast, in this type of experiment, we can use user-defined threshold. We again show that our method prioritizes accuracy over speed up, and we encourage you to check the detailed comparison in the paper. To sum up, in this paper, we proposed automatic termination for HPOR that can be actually used in problems apart from HPOR in general in Bayesian optimization. And this criterion, it adapts problem, and in its core, it uses discrepancy between true HPOR objective, which is generalization performance, expected loss, or Bayesian optimization objective, which is here validation loss. We draw the attention to overlooked problem of overfitting in Bayesian optimization with respect to validation data, and we provide a rich set of experimental results on range of viewer and architecture research problems. For more details, please drop by our poster, and thanks a lot for your attention.